Yet again, educator Carlos Plain of Durham School states, "Certainly I consumed my whole time on Earth cultivating a particular theory of the universe, and by, the theory is being tried. I invite that, since that is how we push ahead. That is the means by which we make strides in science. The James Webb Space Telescope is disturbing a lot of what has been viewed as truth in cosmology over the years. Another ultra-deep image shows that we have committed errors in cosmology. The telescope, which was supposed to show us the first stars of the universe, is transforming into a foe of the past perspective and may present to us an entirely new science. Not all experts are cowering in fear at the new realities. Various specialists welcome these developments, as it has long been evident that something was wrong with our old theories. The variations in the estimation of the expansion speed of the universe alone should have shaken researchers' understanding years ago. Yet, instead of interpreting the warnings accurately, they adhered to old hypotheses. The cosmic microwave background radiation, CMB, considered the oldest light in the universe, was created around 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to form stable hydrogen atoms. Experts call this development reionization, which made the universe transparent to light. The CMB was first discovered in 1964 by American physicists Arno Penzias and Robert Wilson while they were working on a new type of radio antenna technology. This discovery was long regarded as one of the strongest pieces of evidence for the Big Bang theory, earning Penzias and Wilson a Nobel Prize and a significant place in the history of cosmology. The CMB supposedly offers a snapshot of the young universe, with small temperature fluctuations providing critical information about the conditions shortly after the Big Bang. Specialists used the CMB as a reliable benchmark for fundamental measurements of the universe to estimate the expansion rate of the universe. The astronomer Edwin Hubble had already calculated this expansion in the late 1920s, discovering that distant galaxies move away from us, with their speed proportional to their distance. Today, these observations are known as the Hubble law or the Hubble constant. Hubble didn't have access to the advanced measuring methods available decades later, which led to a recalculated expansion rate, generally lower than Hubble's original figure. Later specialists recalculated the rate using Type Ia supernovae as standard candles, celestial objects with predictable brightness that could serve as reliable measurement points. Measurements using the CMB suggested an expansion speed of around 67 km per second per megaparsec, while those using supernovae suggested about 74 km per second per megaparsec. What does this discrepancy in determining the universe's expansion speed really tell us? Did you know that this error has been known since the 1990s? Since then, researchers have suspected that something might be wrong with the CMB measurements, the methods of estimation, or the very concept of the universe's expansion. The inconsistency between these different estimates of the expansion rate is known in science as the Hubble tension or SAA tension. The implications of this tension are enormous, suggesting that critical aspects of how we understand the universe may be incomplete. For a long time, experts were perplexed. However, since the James Webb Space Telescope went online, it has provided scientists with groundbreaking data that might now shed light on the issue of the universe's expansion. Galaxies so old and mature that their formation should theoretically have begun before the Big Bang are overturning old astronomical assumptions. Researchers no longer talk about measurement errors or discrepancies but instead refer to this as the greatest crisis in modern astronomy. Not only could the expansion rate be incorrect, but the entire concept of expansion, or even the Big Bang itself, is now being questioned. A series of images provide evidence of a universe very different from what we have long assumed. The Hubble tension was the first clue. Experts who still believe in old theories now face a pressing issue. Do we truly know the universe? Many specialists stand at the ruins of their once prized theories, exploring space with trepidation, no longer understanding what they find. Considering the crisis in science, we must ask ourselves, what do we actually know about the universe? To answer this, we need to understand how science functions. Theoretical scientists use a complex web of mathematical models, precise data, and logical reasoning to draw conclusions from the general to the specific. Their insights come from a combination of observations, experimental results, and theoretical calculations. The term theory itself suggests constructs and ideas rather than absolute truths. The most tangible data we have are the images provided by telescopes, sound waves, and radiation captured with radio telescopes, as well as data from neutrino detectors or gravitational wave observatories. With the James Webb Space Telescope, we now have an instrument that can break down the oldest light into individual frequencies and analyze it in extraordinary ways. Webb can reveal the dominant elements in galaxies billions of years ago, their mass, and the number of stars they contained. However, Webb also has limitations. For instance, it cannot always confirm whether we are observing galaxies or black holes with massive accretion disks that shine as brightly as galaxies. We must confront the reality that our science has long accepted too many possibilities as facts while dismissing alternative explanations. For a long time, research has been confident in its accuracy. The latest discoveries from the James Webb Telescope are crucial hints for replacing theories with new insights, as has repeatedly happened throughout the history of science. Specialists are now in a holding pattern. The discoveries are too surprising, and many struggle to develop new explanations. The revelations shake the foundations of our physics, unsettling many scientists. The current models of physics are still largely based on Isaac Newton's work from the 17th century. His laws of motion and gravity were the bedrock of our understanding of the physical world and the universe for centuries. Newton's laws describe the motion of objects under normal conditions and work well on Earth. However, in space, his ideas required expansion, largely achieved by Albert Einstein in the early 20th century. Einstein's special theory of relativity, published in 1905, revolutionized our understanding of space and time, showing that they are interconnected and depend on the observer's motion. His general theory of relativity, published in 1915, extended these ideas with mathematical descriptions of gravitational anomalies caused by the curvature of spacetime by massive objects like stars or galaxies. While Einstein's theories were accurate in many respects, he knew their limitations and yearned for a world equation that he never achieved. Neither has been. To this day, no scientist has succeeded in achieving this. Where is the missing step? Wouldn't it be fascinating to know where it lies? Michio Kaku, a renowned astrophysicist, recently remarked in an interview that solving this issue would surely earn a Nobel Prize. Could it be that scientists have overlooked potential misinterpretations, or that our telescopes are to blame? Dark matter and dark energy are at the forefront of suspects for the true causes of the cosmological crisis. Our current models of the universe suggest that dark matter and dark energy constitute around 95% of the universe. However, clearly, their certifiable presence has never been shown, and they presumably won't exist in any way, shape, or form, requiring different explanations for the universe's turn of events and the elements of frameworks. Alternatively, they could have properties we don't yet realize. One idea is that the genuine properties of dark matter and dark energy have changed over time, possibly showing some kind of knowledge. Gravity is another theory to be explored. This force, provoking interest through mass or curvature in spacetime, has not yet been demonstrated. The considerations of spacetime curvature mostly originate from Einstein and have been validated extensively. However, we cannot dismiss the possibility that gravity has surprising properties compared to what we thought, or that another influence causes the gravitational pull between objects. Over the years, several constants have been established in cosmology and astronomy as universal values. The study of the universe has always been a journey marked by our persistent quest for understanding and discovery. From ancient civilizations observing the stars to modern space telescopes probing the depths of the universe, each step in advancement and theory has unveiled new mysteries while challenging established beliefs. In the realm of cosmology, the James Webb Space Telescope, JWST, stands as a beacon of scientific progress, promising to transform our understanding of the universe's origins and evolution. Launched with extraordinary capabilities, JWST represents a breakthrough in observational astronomy, designed to look further into space and time than ever before. One of the primary goals of JWST is to study the cosmic microwave background, CMB, radiation with unprecedented precision. The CMB, often referred to as the afterglow of the Big Bang, provides a glimpse of the universe as it existed only 380,000 years after its formation. This relic radiation carries critical information about the universe's fundamental conditions, including its temperature variances, which are crucial for understanding the development of galaxies and large-scale structures. The discrepancy in the calculated values of the Hubble constant, known as the Hubble tension, has been a persistent challenge, suggesting a lower expansion rate of the universe. Observations using Type Ia supernovae and other cosmological tests yield a higher value. The tension implies that our current models may be incomplete or that there are fundamental aspects of the universe's development that we do not yet grasp. Beyond the Hubble tension, JWST has the potential to reveal insights into other cosmological mysteries, such as the nature of dark matter and dark energy. These elusive components are hypothesized to comprise most of the universe's mass-energy content, yet their presence remains inferred indirectly through gravitational effects rather than directly observed. JWST's ability to study the distribution of matter and energy across galactic history could provide critical insights into the properties and evolution of dark matter and dark energy. Additionally, JWST's observations of distant cosmic systems and celestial bodies offer a glimpse into the grandeur of stories that were previously inaccessible. By examining the light from ancient galaxies, astronomers can trace the development and evolution of stars and cosmic systems over billions of years. These observations not only shed light on our understanding of galaxy formation but also constrain the processes that shaped the early universe. The telescope's advanced instrumentation, including its suite of infrared detectors and spectrographs, enables scientists to analyze the chemical composition of distant galaxies with remarkable detail. By measuring the abundances of elements like hydrogen, helium, and heavier metals in ancient star-forming regions, JWST can unravel the history of chemical enrichment in the universe. These insights are crucial for refining models of stellar evolution and understanding how galaxies have developed their properties over cosmic time. One of the most exciting aspects of JWST's mission is its ability to detect and characterize exoplanets, planets orbiting stars beyond our solar system. By observing the faint infrared light emitted by these distant worlds, JWST can analyze their atmospheres and search for signs of habitability or even indications of life. This capability marks a significant milestone in our mission to identify potentially habitable planets and understand the diversity of planetary systems throughout the universe. In addition to its scientific objectives, JWST represents a testament to international collaboration and technological innovation. The telescope's development involved contributions from multiple space agencies, including NASA, the European Space Agency (ESA), and the Canadian Space Agency (CSA), highlighting the global effort to push the boundaries of space exploration. From its multilayered sunshield, designed to protect sensitive instruments from solar radiation, to its state-of-the-art optics optimized for infrared observations, JWST embodies decades of research and engineering expertise. The journey to launch JWST was not without challenges. Initially envisioned in the aftermath of the Hubble Space Telescope's success, JWST faced numerous obstacles, including budget constraints and delays, that tested the resolve of scientists and engineers involved in its development. However, determination and ingenuity prevailed, culminating in the successful launch of JWST atop an Ariane 5 rocket in December 2021. Now operational in its designated orbit around the second Lagrange point, L2. Approximately 1.5 million kilometers from Earth, JWST is poised to embark on an unprecedented journey of discovery. Unlike its predecessor Hubble, which operates primarily in the visible and ultraviolet frequencies, JWST's infrared capabilities allow it to penetrate vast dust clouds and observe objects obscured from optical telescopes. This unique vantage point offers a comprehensive view of the universe across a wide range of frequencies, from near-infrared to mid-infrared regions. The scientific community eagerly anticipates JWST's first observations, which promise to unveil a wealth of new discoveries and insights into fundamental questions about the universe. From studying the conditions of the early universe to investigating the atmospheres of exoplanets, JWST's observations will shape our understanding of astronomy, cosmology, and planetary science for decades to come.